Alright, welcome back to part 2 of our lecture about static stability. Now, I told you static stability is going to be the one that's going to be important in Module 4. It's going to be the one that's going to be talking about like how we decide on the wind profile, how winds are going to be changing with respect to height and so on. And we said that static stability is a property of the atmosphere, of a layer of the atmosphere. You need to know things like the temperatures and the winds and so on inside the layer to determine the stability. Static stability is going to be determining what happens if an air parcel within that layer is nudged, maybe a little bit up, maybe a little bit down. If we slightly change the altitude of that air parcel, just because, it had to go over a hill, or it was lifted a little bit by a cold front, what happens then? Well, let's consider this situation. Here I've got a layer of the atmosphere drawn. We're taking, that picture in the background is part of the story here. So I've got like the bottom and the top of some layer of the atmosphere. Maybe that's the Ekman layer or something like that. And let's just define, hey, there's some air parcel inside of there. Now, what's going to happen if we take that air parcel and we displace it vertically? Well, I can think of two different senses of this word. What do I mean if we lift the air parcel? I mean, one thing is what's going to happen to the air parcel itself, and the story is its temperature is going to change. Anytime we lift an air parcel, whether it rises on its own or we lift it, the temperature of the air parcel falls. Anytime you lift an air parcel, the temperature of the air parcel falls. It has to do with the fact that as you lift the air parcel, it's encountering air that is at lower pressure than it is. So the air parcel expands, but expansion is work. Work is energy, and it causes the air parcel to cool as it does work to expand. It doesn't in general have to stay the same temperature as the air around it. You can see on this example here, as we lifted this air parcel, the air parcel's temperature was not the same as the environmental air through which it was moving. Remember, we use this word environment to mean like the air around the air parcel. We don't mean the word environment in the context of like save the whales or something like that. Okay, this is just the air around, the surrounding air. Similarly, by the way, anytime we lower an air parcel, the temperature of the air parcel is going to increase. Okay? As we lower the air parcel, it encounters air in its environment that is at a higher pressure than it is. The air in the environment crushes the air parcel. The temperature of the air parcel goes up. So, okay, we just as long as we have some rough sense here, when we lift our air parcel, when we nudged it upward, we know its temperature is going to decrease. If later we do something to nudge the air parcel downward, its temperature is going to have to increase. Okay, pretty straightforward. But what does that mean for how the motion of the air parcel is going to change? Is this air parcel going to continue to rise once we've nudged it upward? Is this air parcel going to sink back down to its original altitude once we've nudged it upward, etc.? And the answer is it depends. It depends on this property, the static stability of the layer. Now, we're going to say that there's going to turn out to be three different categories, if you will, to the static stability. A layer of the atmosphere can be statically unstable, statically stable, or statically neutral. If this layer that I'm talking about here with this, bounded by these two dashed lines here, is statically unstable, then once I nudge that air parcel away from its original altitude, it's going to continue accelerating away from its original altitude. So if I nudge that air parcel upward slightly, it will continue to rise if that layer is statically unstable. And that's going to be true, by the way, if the layer is statically unstable. If I lower the air parcel, if I nudge it downward for whatever reason, the air parcel will continue to accelerate downward if the layer is statically unstable. We would say, by the way, the word we would use here is that the stability of that layer is encouraging further vertical motion, just to throw some parlance there at you. What about if this layer of air were statically stable? Now again, we haven't yet decided how we're going to know if the layer is statically stable or statically unstable, but what does it mean if it is? Okay, well, let's say this layer were statically stable. Well, then we know from our understanding of what the word stable means that apparently the layer is going to be resisting change. And that's exactly what's going to happen. If the layer here is stable, when we nudge that air parcel upward, it's going to want to return back to its original altitude, like what happened here in this diagram that I have up there. I nudged the air parcel upward a little bit. Once I stopped doing that, the air parcel just returned to its original altitude. And that's going to be true, by the way, whether the original nudge was upward or downward, as long as the layer is statically stable. And so, in this case, I nudged the air parcel downward a little bit, but because that layer it was moving through was statically stable, then as soon as I stopped nudging it downward, it just returned to its original altitude. It was resisting further vertical motion. which is, again, just throwing some vocabulary around as to how we think about it. Well, if we have statically unstable and statically stable, there is an in-between situation called statically neutral. When a layer of the atmosphere is statically neutral, when I nudge an air parcel and give it a little push upward or a little push downward, it just stays wherever I left it. So like here I have a layer of the atmosphere that is, again, statically neutral. We don't yet know how we decided that, but if I told you in advance this layer is statically neutral, you now know what would happen. You lift an air parcel, no problem. It's not going to fight you, it's not going to help you. The layer will just leave the air parcel wherever you put it. Similarly, if we lower the air parcel with like a nudge downward, once we stop nudging it, it'll just stay where we put it. Okay? The layer is neither helping, neither encouraging vertical motion, nor resisting vertical motion. So static stability is going to be a property of that layer, and it's going to determine what's going to happen if an air parcel gets vertically displaced by any of the thousands of things that have been going on in the atmosphere, especially near the surface of the Earth. So I guess the static stability sounds kind of important because it's going to be telling us where air parcels are going to be rising and sinking, or returning back to their original altitude, or whatever. We better sort out this business of what determines the static stability of that layer. Okay, well, kind of a related question we'd have to understand first is, why would an air parcel rise or sink anyway? I mean, if I've got an air parcel and it's at some location surrounded by some environmental air around it, what determines whether it rises or sinks? I mean, I said, yeah, I nudged it at first. I mean, that's just sort of a thought problem thing. I mean, maybe it rose over a hill or something like that. The question is, then what? Well, the story is about buoyancy. If an air parcel is going to rise on its own if it is warmer and therefore less dense than the environmental air around it. We say that the air parcel is positively buoyant. The air parcel is going to sink on its own if it is colder than the environmental air around it and therefore more dense than the environmental air around it. We would describe that air as being negatively buoyant. Now, let's see how that applies to our situation with regard to the stability. Now, to help us visualize what's going on here, I've actually colored in our layer of the atmosphere here with like red warm colors down near the bottom of the layer and colder colors up near the top, recognizing that most of the time in the troposphere that's the way it works, right? I mean, the temperature is usually warmer at the bottom, and the higher up you go, the colder it gets. And from here on out, I'll color in the air parcel whatever color I want it, whatever temperature I think it is. So like here I'm starting off with my air parcel, and I have it colored the same color as the height at which it is. So like I'm saying that this air parcel is the same temperature as the air around it. It's neutrally buoyant. This air parcel is neither, trying to float away nor sink down on its own. Now I nudged it upward. Now in this particular case, my air parcel is cooling. Always air parcels cool as they expand. Anytime you lift an air parcel, it cools. But if it stays warmer than the air around it, and that's what I'm trying to illustrate here, is that air parcel is like, it's a warmer color than the air around it, it's going to be able to be positively buoyant and just keep rising on its own. Something about the stability of the layer is going to be about deciding whether these air parcels are positively buoyant or negatively buoyant once they have been nudged or displaced. So it will keep rising off from its original altitude. Now, in order to figure this out, we need to know how much that air parcel is cooling as it rises. Happily, that turns out to be a really basic thing. The rate at which an air parcel cools as it rises is a known constant. It's called the dry adiabatic lapse rate, or DALR. It's got a symbol, capital gamma, lowercase d, gamma d. It's just the rate of change in temperature with respect to height, dTdz. It's got a negative sign in front of it for the sign convention's reasons. As it happens, that's something you would derive in like a thermodynamics class, but it turns out to be a constant. It's actually the ratio of two constants in the atmosphere. Cp is the specific heat of dry air. You don't need to know that number. Well, I think you do actually use it in one or two of the homework problems, but whatever, it's in the book. And G is just the gravitational constant, 9.8 meters per second per second. And it works out, because C sub P is right around 1,000, you end up with 9.8 degrees Celsius per kilometer, or that very small number of Kelvin per meter to put it into proper scientific units. In other words, for every kilometer I lift up my air parcel, its temperature should decrease by 9.8 degrees Celsius, effectively 10 degrees Celsius. Okay, a lot of times in classes we just assume this number is equal to 10. But it's just a constant, which is so handy. It's astonishing to me that this just works out to a constant. On the other hand, remember, now we're trying to compare the temperature of that air parcel to the temperature of the air around it. We need to know the temperatures of the air around it and how they're changing. Now, that's something we measure. We get that from like weather balloons and radiosondes, and from that information, like the temperature at the top of the layer and the temperature at the bottom of the layer and how far it is from the top of the layer to the bottom of the layer, we get the environmental lapse rate. In other words, like the measured difference in the temperature at different heights. And the symbol for the environmental lapse rate, or ELR, is just gamma. So gamma is the measured environmental lapse rate. Gamma D is the dry adiabatic lapse rate, and it's a constant for the atmosphere. And you can see then there's a simple way then to compute the environmental lapse rate. You just take the difference between the temperature at the top and the bottom of the layer, and you divide by the distance between the top and the bottom layer, and then there's a negative sign in front of the whole thing. Alright, with those two pieces of information, as long as you can figure out the stability. Because see, as long as that air parcel is rising doesn't cool as fast as the environmental air around it is cooling, it's going to be warmer than the air around it. It's going to be lighter than the air around it, and therefore it's going to be positively buoyant around it. Which means we get a very, very simple rule for determining the static stability of this layer. If the environmental lapse rate gamma is greater than the dry adiabatic lapse rate gamma D, the dry adiabatic lapse rate gamma D, we can always say that this layer is statically unstable. Oh. So just taking observations that we get from like a weather balloon or something like that, we can determine what the stability of this layer is. We can say, in this case, because the environmental lapse rate was more than the dry adiabatic lapse rate, we now know that this layer is statically unstable. This works for sinking motions too, by the way. As long as the air parcel is sinking, it is warming, but if it's not warming as much as the environment, it will stay cooler than the environment as it sinks. At any given moment, it will be colder than the air around it, it will be more dense than the air around it, it will want to continue to accelerate downward, it will be negatively buoyant. So again, in this situation, if the environmental lapse rate gamma was greater than the dry adiabatic lapse rate gamma D, we had a situation where this layer was statically unstable. Okay, all of that required the temperature profile that I had drawn on there, where it was warm near the bottom of the layer and cold near the top of the layer, but that isn't what we always observe. Let's say on a particular day we launched a weather balloon and we saw something like this, where it was actually colder at the bottom of the layer and warmer up near the top of the layer. That happens. You might remember that term from an earlier module. That's a temperature inversion. A temperature inversion is a layer in which the environmental temperature increases with respect to height. And that happens sometimes. Especially at night, that can happen. So let's say we measured that. Now, once again, we're going to be using the colors of that layer to give us at least kind of a sense of what the temperature is at different heights in the layer. And I'm going to keep coloring in my air parcel to tell you what temperature it is. So let's take that air parcel and just say, some reason or other, I nudged it upward. If I nudge that air parcel upward, it's going to cool, because all air parcels cool when we lift them. It's going to cool at the dry adiabatic lapse rate. But the environment was actually getting warmer as you went up. No doubt about it. This air parcel is colder than the air around it, it's more dense than the air around it, and therefore it's going to want to sink. It's going to become negatively buoyant and just sink back down to its original altitude. Oh, that's pretty slick. And that's going to happen anytime that environmental lapse rate turns out to be less than the dry adiabatic lapse rate, including anytime when we have a temperature inversion, because when you have a temperature inversion, the environmental lapse rate is actually negative. So, like in this situation I have here, the environmental lapse rate would be like a negative number. Well, negative numbers are always less than the dry adiabatic lapse rate, which is 10. So, anytime your environmental lapse rate is less than the dry adiabatic lapse rate, you're going to have a situation where that layer is statically stable. So here's your second of your 3 rules for figuring this business out. If you do a calculation in the homework or on the test or something and you find that the environmental lapse rate is less than the dry adiabatic lapse rate, if gamma is less than gamma D, then you know your layer is statically stable. And this works for sinking motions too. If I nudged my air parcel downward, it would warm, because all air parcels warm when they are nudged downward. Then, well, clearly, since temperature around it is getting lower the lower you go to the ground, this air parcel is clearly, this kind of pinkish colored air parcel here, is clearly warmer than the air around it. Therefore, it's going to be positively buoyant and it's going to rise back to its original altitude. Once again, showing an example where as long as the dry adiabatic lapse rate is greater than the environmental lapse rate, or I have it written the other way around, if the environmental lapse rate is less than the dry adiabatic lapse rate, you get a layer that is statically stable. I did that example of statically stable conditions with a temperature inversion, but it wouldn't have had to have been. Like here I have another layer colored in, you might not be able to see, but it's almost isothermal. The layer is almost the same temperature throughout the layer, but actually it is a little warmer and pinker towards the bottom and a little bluer toward the top, and my environmental lapse rate here is probably pretty close to 0. The temperature is changing only a little bit with respect to height. Well, numbers near 0 are definitely less than numbers near 10, right? The environmental lapse rate is definitely less than the dry adiabatic lapse rate here. So when I lift that air parcel and it cools, it's definitely colder than the environment around it, and it's going to want to sink back down. We're still statically stable. But what about that middle situation? I mean, we talked about statically stable and statically unstable, but we know that there's this thing called statically neutral. Well, for the layer to be statically neutral, the temperature profile, the environmental lapse rate, has to be just right. It could be, though, we could have adjusted the temperature profile in that layer, which I indicated by the colors in that layer there. We could set them so that they were just right, so that when I took an air parcel at its original height, where it was its original color, and I lifted it up to some new height, just nudging it, the change in temperature it experiences is exactly the same as the change in temperature of the air around it. And now it's exactly the same temperature as the air around it. There's no particular, it's exactly the same density as the air around it. It's got no particular negative or positive buoyancy. It's neutrally buoyant, and it'll just stay where we put it. Now, that is going to then be an example of a situation where the environment is statically neutral, where a layer of the atmosphere is statically neutral. It's going to happen any time the environmental lapse rate happens to be equal to the dry adiabatic lapse rate. So if gamma is equal to gamma d, the layer is statically neutral. Now you might think, what are the odds of that happening? But as you're going to see in a later part of this module, part of this lecture, that actually happens a lot. That's a normal situation a lot of the time. Seems like it'd be hard to hit that, right? It seems like it'd be hard to get the layer to be exactly, its environmental lapse rate to be exactly the dry adiabatic lapse rate, but it's not so hard at all. Now again, this can work, statically neutral applies just as well to rising motions as to sinking motions. If I took that original air parcel at its original altitude and forced it to sink, like any air parcel, it will rise its temperature will rise as we lower it, as we lower the air parcel closer to the ground. So the air parcel got warmer, but the environment around it was getting warmer too, and in fact at exactly the same rate per kilometer. And so once we got to this new altitude, the air parcel was exactly the same temperature as the air around it. There was no particular reason for it to rise or sink because it's neither positively nor negatively buoyant. And as a consequence, the air parcel just stays where it was. It's still just statically neutral. This means that there are basically three little rules that you have to remember if you want to figure out the static stability of a layer. You have to compute the layer's environmental lapse rate, ELR. Well, that's not such a big deal. It's just arithmetic. You take the temperature at the top minus the temperature at the bottom, and you divide it by the distance between the two, and then there's a negative sign in front of it. Big whoop. Then you just apply these three rules. If the the environmental lapse rate is more than the dry adiabatic lapse rate, your layer is statically unstable and it tends to encourage vertical motion. If your environmental lapse rate is less than the dry adiabatic lapse rate, your layer is statically stable and it tends to resist vertical motion. And if it just so happens that the dry adiabatic lapse rate and the environmental lapse rate are exactly the same, your layer is statically neutral and the layer neither encourages nor discourages vertical motion. Now this is pretty neat. It's just a simple little trick to figure this out. A little bit of arithmetic and memorization of three rules. Not that big of a deal. But it turns out there are even better ways to determine the static stability of the layer, which is what we're going to be doing in the rest of this lecture. But before we do that, let's take a few moments to do a few more questions. Question 3. Suppose that a layer of the atmosphere was statically unstable. If I took an air parcel from within that layer and I lift it up a little bit, if I nudge it a little bit, the air parcel will be blank than the environmental air around it and blank buoyant. Colder or warmer than the air around it and positively or negatively buoyant. Make a choice from those 4 combinations and get a little feedback before you move on to question 4.